Okay, so let's construct this TAB tensor, the object that tells us about TAB lower or TAB upper, or of course we could have TAB with the diagonal terms, one upper, one lower. But this is the object that tells us about this about the stuff that curves space and time. So we sort of imagine a bunch of objects of mass moving around, and maybe we can think of this continuously. So we have sort of a region of stuff with some density, density rho m, and there's sort of a natural way to build this object up. There's a 4 velocity for the particles, and in the continuous limit, there is a continuous 4 velocity that describes the 4 velocity at some point for this spread out stuff over space. So, if we are locally following the fluid, this is some kind of fluid, then VA has 1, 0, 0, 0 components. That's the 4 velocity in the rest frame, and so in the rest frame we want some stuff that's just sitting there, and of course it has energy due to mass, right? We want mc squared energy kind of thing, but we're talking about density, so we have an m over volume c squared kind of object, and so that's a density rho m c squared kind of object. And so we can say T00, it's built out of these objects here, should look like that, and this sort of gives us a hint as to how to construct TAB more generally, where the fluid velocity isn't 0. So it should be something like rho mc squared, VAVB, where we have a rho mc squared times, V0, V0, V1, V0, V2, V0, V3, V0, V0, V1, V0, V2, V0, oops, V0, V3, diagonal terms, V1, V1, V0, V1, V2, V1, V2, V1, V3, V1. We are 0, 2, so we want V1, 2, V2, 2, goodness, VV, VV, and V2, V3. What happened here? V3, sorry. V2, we're adding on that one, so V3, V1. Here we have, so it's V3, V2, and the last row is V1, V3, V2, V3, and V3, V3. So that looks like the kind of object that we're looking for, and we can check that the conservation laws are going to be these rows. So dt0b with respect to xb is equal to dt00 with respect to x0 plus dt01 with respect to x1 plus dt02 with respect to x2, and so on. And so we can see that this looks like the thing that we needed before, the conservation of energy and momentum. This is d by dt, divergence of the momentum, equals 0. And we can then look at these other rows and see that the time derivative of the first term, right, there's a gamma factor here, and there's a velocity in the one direction, velocity in the x direction. So we have dvx by dt, and this looks like the time derivative of the momentum, right, because we have mass here. And so that looks like a force. So force in the x direction, force in the y direction, force in the z direction, and that's part of the conservation laws. So this is just sort of to motivate the idea that we are capable of producing conservation laws that we need as a way of constraining our G, A, B. We need this object, and so this is going to be directly related to this object, and the covariant divergence of this, as we said before, needs to be equal to 0. This is the thing that we're going to start looking for. We don't have too many options. And then we won't worry too much about this, because ultimately we're going to look at situations where here's where the distribution of matter and energy is that dominates. And so here we have that TAB is not equal to 0, but we will be looking at finding the curvature in regions like this, like at a point here. Right, so if we use coordinates that spherical coordinates, spherically symmetric coordinates, right, some radial coordinate r, there is no matter there, but that doesn't mean that space-time there isn't curved, because there's this stuff here. Right, in the same way that, we say the divergence of the electric field is 0, it doesn't mean that the electric field is 0 at some location where the charge density is 0, because the charge could be somewhere else.